Hello everyone. In this video, I want to show you how to find moving objects in MATLAB using optical flow, and we're going to use the FarneBack algorithm, which is a dense algorithm. So it gives you optical flow for each and every one of the pixels. And I have done this method in OpenCV here. I just want to show you how to use built-in functions in MATLAB to do that. So first I create a video reader object and I start at time of 10 seconds. And I pick my optical flow method. So optical flow for me is optical flow FarneBack. There are other methods. There is Lucas Canade and there is Hornschnock. And I use FarneBack, which is kind of the denser one. Now, if you run this portion, look what happens. Let me just run this portion for you. So this optical flow object has the following properties. It has 3 layers or 3 pyramids. Each time the images are subsampled or scaled down by a factor of 2, so they go to half a scale. 3 iterations, of course, and the neighborhood size is 5 by 5 around each pixel to calculate the intensities, and the filter size is 15. So you know why we use pyramids. If you used my other videos on optical flow, you know that if when we use the, we call the intensity constancy equation, right, where I at, basically it's this equation if I want to show you. So it's this one that I sub x, correct, times u plus ab sub y times v plus I sub t equals 0, correct? That's this equation. When we derive this equation, we assume that the time frame and the displacement of pixels between one frame and the next is small. We use dt, dx, dy. So that approximation is only good when the time frame and the displacement of the pixels are very small. Now, many times the frame rate is not high enough that your car or whatever object, pedestrian, anything that you're tracking moves several pixels, not just one or a fraction of a pixel between 2 frames. In that sense, if we use this fundamental equation, this is not going to be valid anymore. So what we need to do is to use a pyramid and bring the original frame down to much smaller sizes. In those smaller sizes, hopefully, the displacement of the object or the pixels of the object between one frame and the next is small enough that this equation is approximately valid. So we calculate optical flow U and V in that smaller version of the image, then go to the next level in the pyramid, and we warp that next level image with the U and V we found from the previous image, recalculate U and V at this next level, and keep doing that until we come back to the original size, and we keep updating U and V, going from top of the pyramid to the back to the bottom of the pyramid with where the original frames are. So this is good when your pixel motions are large enough between 2 frames, or frame rate is very not large enough for the motion of the object. So I get that. If you want, you can change any of those. So if, for instance, you have basically so much pixel motion between the frames, I would use 5-level pyramids or 10-level pyramids. Now, of course, it's going to make it a lot slower, but you have this extra option to pass to it here and say, for instance, here you say that the number of levels of the pyramid, you can see that here, that the number of pyramid levels, right, this is equal to 5 as opposed to 3. Okay, so you can do that as well here. So once you determine this optical flow calculator, here I create a figure. This is an interesting command, move GUI. It moves the figure to somewhere exactly in the screen. Because sometimes I'm sure you have experience if you use computer vision toolbox, you create a window, like for instance for video player, and then what you'll see is that window is kind of half of it in your screen, the other half is outside the screen, and you have to drag it manually and bring it somewhere to the center or somewhere. right? So this command will automatically do that for you. It brings that figure, if some portion of it is outside, it brings it so that it's entirely on the screen, so you can see the whole figure. That's a nice command. I just decided to add that for you here. Then I create a panel on that movie, which has the title FarneBack Optical Flow Vectors, and I put it at a specific location, and that is added to that figure H. And now I convert that panel into an axis and an axis handle here, hplot, so I can later use that axis. I want to update some stuff on that basically axis handle. So what I do is I use a while loop again and has frames, so I read through each and every one of the frames of the video. I get that frame using the read frame. I resize it by a factor of 2 to make it big enough, convert it to RGB to gray. Remember, anytime you use optical flow, the image has to be grayscale. And then I use the built-in function estimate flow, where I pass to it the optical flow calculator and the current frame. Okay, and it gives me the vector flow u and v. That's the vector flow u and v. Now you see here, I'm not using the step command. In 2 of my previous videos, you see whenever I wanted to apply a method on some data, I used step, not for optical flow. For optical flow, the way to apply it is called estimate flow. So now I show the frame, and then I use a hold on, and then I use the plot command. This is not the regular plot command. This is the plot command that is for showing optical flow vectors. Although it's the same name, plot, but this is a little bit different. If you want to know more about it, go to this link and learn more about this. So you show the vector field u and v, and then if the vector field is too dense, there are too many vectors everywhere, you can use a decimation factor, and this will decimate. Basically, when you say 5 by 5, only in each window of 5 by 5 pixels, instead of 25 U's and V's or 25 arrows, it only shows a single arrow. Okay, so it decimates every 25 arrows to 1 arrow and makes the arrow vector not as dense, so you can see them. And then you can make those arrows a little bit bigger, so you can visualize them bigger, because sometimes if the magnitudes of those U's and V's are small, this magnitude of these arrows are going to be the same, small. So here you use some scaling factor to show them better. And now I want to show this vector field where? On the original, look, axis, on the axis handle. I say the parent is hplot. So what am I doing here? On this figure, on this axis, first I show the frame, then on the top of that with hold on, I show the vector field. So the vector field is going to be overlaid on the frame. And I use hold off, so when I go to the next frame, it doesn't keep holding on. I use some pause to slow it down. And finally, I release what? I release the optical flow. And of course, I have to release, like the other times, the video reader, right? Because these are my objects that I'm using. So let's go ahead and see what happens when we read the frames and show the optical flow over the frame. Okay, time 10, it starts, and you clearly can see, let's see if I can maximize this, you clearly can see the arrows in blue over the car, right? You see they're all on average showing a forward motion, you can see. And of course, there are some artifacts here and there because optical flow is not actual motion of the pixels, it's apparent motion of the pixels. So if there is lighting changes, like in this scenario, although the camera is fixed, you still might see some arrows. Now, mostly they are very small, and if you find the magnitude of these arrows and apply a threshold, mostly the dominant objects are going to be the cars, but you know, somewhere here and there, you might see some artifacts as well, okay? And so if on that blob that you get from the binarizing the magnitude of UV vector, you go ahead and do some morphological operations like BW area open or IM close and something, you might be able to get rid of some of these artifacts. but clearly, and use IMFill to fill in these holes. You see in these regions, they are not showing as big. The rest of it, you clearly see the forward arrows showing the direction of motion. Okay, so here is how you can calculate optical flow on frames of a video and overlay it on the image using the FarneBack, which is a dense method, and it acts actually very nicely. So hopefully this video was useful to you. Look for the code. I'm gonna upload it and give you the download link for the code under video description. Hopefully you enjoyed this video. I'll see you in the next lecture.